Hello. Hey, Audrey. How's it going? A dog. Got the assignment here. So this is the guess from the UT school. Some unit 3, lesson 1. So evaluating here. So I'm gonna help you out. There's some. Hopefully, I can explain it pretty well. Okay. So given. Let's see. Zoom. Given that you have some quadratic here, so some f of x equals x squared plus 10x plus 28 in standard form, convert this to vertex form using completing the square and show work to get credit. So let's do a little recap before we get into this. So I'm going to recap here. So we're dealing with quadratics here. Quadratics, of which there are a couple forms. So we have standard form for quadratic, and we have also vertex form. So let's kind of compare the two. So standard form, so f of x, some function here, is equal to ax squared plus bx plus c. There's standard form for a quadratic. This is standard form. This is standard form. Then the other form we have is vertex form. Vertex form. And there are a couple ways to go from one to the other. Vertex form is a times x minus h squared plus k. So this is vertex form. Great thing about vertex form is you can tell the vertex immediately. That's why it's called vertex form. Standard form is good for other things, like for solving and finding solutions. Standard form is easier. And so we want to go one to the other. And there's a couple ways to go about it. I'll show you both ways, but for now we'll do the assignment. So we're starting off with this. In the assignment, we want to go to this form. And really what we want to do is we want to, yeah. So we'll do this. We'll do some work here and see if we can get that. Then we'll check it another way. Okay, so let's start off this way. So I'm going to zoom in so I can make it there. So again, I'm starting off with f of x equals x squared plus 10x plus 28. And I want to complete the square. Actually, I do need to go real quick. Let's check back in and make sure we know how to complete the square, what that means. Completing the square you're thinking about here how what does that mean? You're completing the square. You want to have a perfect square trinomial. What does that mean? Okay, let's look at some examples. So let's say I take x plus a and I square that. This is a hypothetical. I have some expression, two variables x and a, and I'm squaring it, right? So what does that mean? Okay, so x plus a squared means x plus a times x plus a. If you were to FOIL that, you get x squared, right? That's your first outer inner last, or this times this. This times that. X times a is ax. A times x is also ax. And a times a is a squared. And then I can combine this middle term here, where this is x squared plus 2ax plus a squared. So this is a perfect square trinomial because you could factor it to this, right? It looks like that, right? These are the same thing. If I see anything in this form, I can rewrite it as this. So if I see anything in this form, I can rewrite it like this. And so the key to going from this form, I'll call that 1, going from form 1 to form 2, is that I need to know what a is. What is a? Notice there's 2a here, there's a squared here. There's 2a there, there's a squared there. Sorry the interruption. I'm at McCallum right now, and they always find a way to interrupt me at the worst possible time. So if I can find this value, the question is, what is a? What is this value? What is a here? If I can do that, then I can complete the square. Our whole goal is to complete the square, right? So actually, I'm going to do it in this paper, and I'll rewrite it in this paper later. So again, what I have, it's a long roundabout way of getting there. F of x equals x squared plus 10x. And I'm actually going to go ahead and it's plus 20. I'm going to write the 28 over here. And I'll show you why. Right, so again, this is the problem we start off with. X squared plus 10x plus 28. I wrote the 28 way over on the distance here. And my idea, again, is I want to know what is A. What is the A value here when I refer to this? What is A value here? Well, it's really just half of this value, right? If this is 2A, then, right, so in this case, right now, if we kind of just pattern match here, in our problem, 10 is equal to 2A. So then A would be equal to 5. Right? A is equal to 5. And so to complete the square here, right, to complete the square here, I found A. A is 5, right? Half of that B value, half of this value, half of 10 is 5. That's 5. I need to square. I need to add 25 right here. I need to add 25 right here. Now this is a perfect square trinomial. So I took half of that value, squared it, and added there. Now, because this is on one side of the equation, right? Normally in algebra you think you can do anything to both sides. You want to maintain balance. Here, we're doing everything on one side of the equation. So to maintain balance, if I add 25, I'm also going to subtract 25. I'm also going to subtract 25. So at this point, I took half that B value, in this case the B, half of that, divided, so that's 5, squared it, add 25 here, and also subtract 25 here. That way you're not actually changing anything, you're just rewriting it, you're rethinking it. And now, this is a perfect square trinomial. So I can go from this form to this form right here. So I can rewrite this whole thing that come down as x plus 5 squared. Right? That's what that equals. And then down here, 28 minus 25, that's plus 3. And now you have it in vertex form. So it was in standard form. You completed the square. You took half of 10. You squared it. You added 25. You also subtract 25 here. And you simplified this to be x plus 5 squared. And then you simplified that. 28 minus 25 is plus 3. And there it is in vertex form. And you can check that. You can always check your work because there's a million ways to check the work here. So let's check the work. Let's do that just to make sure I'm right, because I haven't done this in a second. I haven't done this in one hot second. So let me move this over here. Right, go to Desmos really quick. Here's one of the many ways to check your work is to put it in Desmos. So again, let's think about this. This f of x is equal to x squared. Right, x squared, it was plus 10x plus 28. This is what it was before. Now, the vertex form we got, I'll write that as g. We got x plus 5, x plus 5 squared, plus 3, right? The blue is right where the red was, so we know we were right. So we know that method works. So I know that this is the way to do it. Just for the sake of making sure that I explain it really, really well, I'll do it one more time. So again, all I'm going to do here is I'm going to rewrite this, x squared plus 10x, and I'm going to make some space here. I'm going to move the 28 over. I'm going to take half of that value, half of whatever the b value is here, as long as a is 1. A is 1 here. Take half the b value, which is 10. Divide that by 2. It's 5. I'm going to square that, and I get 25. 25. So plus 25 here, minus 25 there. That way you can maintain balance. This simplifies to x plus 5 squared plus 3. There it is in vertex form, right? So it's 8 points for adding, subtracting the correct values. That's what we did here. We add, subtract. 3 points for factoring completely. Yes, you factor completely. It's x plus 5 squared. 3 points for simplifying. That's it. Woo, that's the answer. We graphed it, and we know that's the answer. We're very positive that is 100% correct. Verify your answer is equivalence. So compare your answer to the given function and include a graph or data table for each. Okay, so how can we verify? How could we verify? You could put in some values. You want a table? I'm going to verify with a table. Okay, sure. Let's verify with a table. So then I'm going to say I'm going to do when x is 0. Let's try with 0. So let's plug in a 0. So then f of 0 is equal to 0 plus 5 squared plus 3. This is now going to be 5 squared plus 3. It's 25 plus 3, 28, right? F of 0 equals 28, right? That's with our vertex form. If we plug in a 0, we get 28. If I plug in 0 with my original thing here, so I'll do it again. I'll say f of 0 is equal to 0 squared plus 10 times 0 plus 28. Now I'm plugging 0 into the original equation. 0 squared is 0. 10 times 0 is 0. Plus 28, you get f of 0 equals 28. Right? So it's the same both ways. So I plug in any value into either of these equations, they'll be the same because these functions are the same. So there's some points there. If you wanted to graph it, you could graph. You're gonna graph both. I don't know how else to verify it other than yeah, that's you graphed it. Here, just for the graph, you want to graph it. It's not that hard to graph this one. You put it in vertex form. The vertex here is that going to be the vertex, right? Because this is from vertex form, so it's just -5. Opposite of that, -5, comma 3. -5, comma 3. So it's 1, 2, 3, 4, 5. 1, 2, 3. Boom. There's your vertex. A -5, 3. Over 1, up 1, over 1, up 1, over 2, up 4. There's your graph like that. They just want a graph. You can give them what they want. So you can verify in a couple ways. You can compare tables, you can compare graphs, you can plug some values in. We compared the graph on Desmos, but because they want to look at it, there's that. Okay. Part 2. Identify the following attributes of this function. Okay, yeah, I didn't look at that. So transformations of the parent function. So again, let's think about this. This is a great concept. The parent function. Let's think about transformations of the parent function. And again, what the heck do I mean by that? So where is the parent function? Let's do the parent function here. So y equals do x squared, right? The green one here is the parent function, right? I don't know why I emphasize function. It's a parent function. If I write this now in vertex form, it looks like this. X, and we want minus h plus k. This is what vertex form is. And really, it should be a there as well. And so normally on our parent function, a is 1, h is 0, and k is also 0. Right? So again, this is the parent function. The green one's the parent function. And so we have to go from the green one to the blue one, we have a couple things that's happening here. First off, we're definitely moving the green one to the left in the negative direction. We're going to move that one in the negative direction. So notice, that's k. Oops, h. I'm moving it over. I'm moving it 5 to the left. Right? This shifted horizontally 5 in the negative direction. And then I moved up 3. So I shifted over 5 to the left. I moved up 3. That's your transformation, right? You shifted transformation here. I'd say shifted horizontally 5 in negative direction. Shift vertically up in positive direction. You can say that a couple of ways. You shifted 5 to the left, you shifted up 3. That's the transformation there. The vertex, again, is at -5, 3. We see that when we graph it, and also when we complete the square and get it in vertex form, that's you tell the vertex. It's opposite of that. So instead of +5, it's -5. There's your k value, +3. So -5, 3. The axis of symmetry. Axis of symmetry is a line that goes right down the middle, right? If I look at this graph, get rid of this. Look at our graph, our blue graph. Oh, didn't want to do that. Our blue graph. The axis of symmetry, well, let's just find the vertex, and we'll do the vertex. So the vertex is at -5, 3. That's our vertex. I'm going to label it. I might call it the vertex. The axis of symmetry is always equal to, it's always a line at x equals the h value, or the x value of our vertex. Right? That's the axis of symmetry. Right there, the green line goes right down the middle. It's always going to be at x equals whatever this value is, the h value of our vertex. Remember, our vertex, we label that h comma k. H comma k. So it's always going to be x equals h. So again, if your vertex is at h comma k, then the axis of symmetry is always at x equals h, which in this case, h is -5. So x equals -5. There is our axis of symmetry. The domain. Domain for a quadratic is always all real numbers. Almost always all real numbers. Here it is all real numbers. You can have like that double line R. If you look at the domain, how wide your parabola is, it's going to keep getting bigger and bigger. It doesn't really quite look it, but trust me, it's going to keep getting wider and wider the more you go up. It's going to infinitely go up, and it's going to infinitely get wider. So the domain is all real numbers. Now the range is different. Is there a low point here? There's a low point here at y equals 3, right? That is the lowest. 3 is the lowest y value you can possibly have. You can be more than that. Like here's up to, about 5 here or 4, or you can, be up what 10. You can y value can be more than that, but it can't be less than that bottom line at y equals 3. So that means that the range, you can say this. You can say y is greater than or equal to 3. That would work. Or you could say the range between 3 and positive infinity, where it can be 3, but it can't be positive infinity. So it can be like a straight bracket, 3, comma, infinity, parentheses. That would be the range. That'd be the range. Okay, let's look at the back. Find the inverse function of this function. Find the inverse function of that one. So first off, it said you want to swap x and y. Just swap x and y. So I'm going to rewrite this, but I'm going to think of f of x here as y. There's no y there. What I'm going to do is I'm going to rewrite this. Okay, I start off with converting it to y. So I'm going to rewrite this x squared plus 10x plus 28. And actually, I think it's going to be easier for us if we actually write it in vertex form. So I'm going to keep going. This is going to be what? X plus 5 squared plus 3. That's the same function. I just switched it over to vertex form. Now I'm going to actually swap x and y. So x will go here. It's going to become y plus 5 squared plus 3. Right? So I rewrote it in vertex form, and then swap the x and y. And now I'm going to solve for y. So I want to get y by itself. So first thing I do is subtract 3 here. Cancels out. Get x minus 3 equals y plus 5 squared. So how do I get rid of the square? Well, how do you get rid of the square? You square root it. So x minus 3, the square root of x minus 3 equals y plus 5. Almost have y by itself. Now you have to subtract 5. You get the square root of x minus 3, that's not a plus, that's a minus, minus 5 equals y. That'd be the inverse, right? I'm going to rewrite this over here now. Rewrite it the normal way. Y equals the square root of x minus 3, all of that minus 5. And then now I can rewrite this as f inverse of x equals the square root of x minus 3 minus 5. Right, there is the inverse written in that function inverse notation. Right, so 8 points for using correct inverse operations. We did that. 3 points for writing the correct answer with proper notation. We did that. This is a 5, by the way. 5. Verify your answer is correct. Make a data table for your functions and make a data table for f of x. Then explain how the inverse shows that. So let's do that. So let's do one for x and f of x. All right, we'll make a table here. So this is for our original function here. Our original function is right here. There's in vertex form. I think it's easier to think about this starting from the vertex. So I want to start at the point -5, 3. That's going to be easier to think about that. And it might be easier to look at it from the graphs. So again, I'm starting at this vertex, -5, 3. When the input here is -5, the output is +3. So I'm here. I'm starting my table. Input is -5, output is +3. Because that's just the point, x and y point on the vertex. Where else do I have a point? Well, I also have a point. From the vertex, we go over 1, up 1, so I should have a point at -4, 4. And I have the same point at -6, 4. Right? These are points on the vertex. These little points right here. I go from the vertex over 1, up 1. From the vertex over 1, up 1. From the vertex, I can also go over 2, up 4. So if this is at, what's that point at? That point is at -5, 3. I also have a point here at over 2, so it becomes -3, 7, right? Yeah, there we go. Now that's one way to do it. I guess honestly the easiest way to show this would be with the table, to actually use a calculator if you have a calculator. Let's do it that way. So y equals, I'll write it again. Figure out however you want. You make it x squared plus 10x plus 28. Look at your table, and here's the values. And the ones we had: -5, 3, -6, 4, -7, 7. So I'm just putting these values in here. That's enough, right? There's the values table. So that's a table to look at x and f of x. Now let's look at a table for x and f inverse. Look at that table. So here we go. I'm going to go to y equals. I'm going to clear that. I'm going to put in this inverse here. So square root of x minus 3 minus 5. And let's graph that. Let's go to 3. So there's a value at 3, -5, 4, -4, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, 4, -5, We'd also have, let's go 7, -3. Let's look at 12. Let's double check 12. 12, -2. That's enough really for me to prove that. So notice here, you have a point at 12, -2, and here you have a point at -2, 12, right? These are inverses of each other. You have a point at -3, 7, and you have a point at 7, -3. Those are inverses of each other. -4, 4, and 4, -4. Those are inverses of each other. So to be an inverse function, the domain and range is switched. So if you have some function that has a domain and range, if you switch that, that's going to be the domain range of your inverse function. So the domain of one function is the range of its inverse, right? That's a really big idea. Really big idea. So you have f of x, and then you have some value, some set here. That's the domain. And you have some set that this is the range. For the inverse, that same set, the range is its domain. And that same domain for this function is its range. They switch. That's kind of a property of inverses and functions. So that's a way to prove it. That's why I proved it with the table. We can see here that with the table that the x and y values, the x and x values are different, right? The last way to prove it with a graph, you want to prove it with a graph, you can do that too. Here's our buddy Desmos again. I'm going to get rid of some stuff, clear it up a little bit, and I'm going to go ahead and put in. Can I do f to the -1? Does that give me the inverse? I'm just testing out Desmos really quick. No, it doesn't do that. Okay. So I'll make a new function. I'll call it h of x. And I'll set that equal to the square root, sqrt of x minus 3 plus 5. No, minus 5. Sorry, minus 5. Minus 5. And it really should be plus or minus. So for my graph, let me do another one here. I'm going to make this j of x. I'm just running out of names. So you could just use y the whole time. I don't know why I do function notation a lot. Negative sqrt x minus 3 minus 5. I'll make this green as well. And then I'll do one more line at y equals x. And I'll make this orange. See how they're inverse of each other? Because they are, if you look at these lines here, they're mirrored over the line y equals x. So that's another truth about inverse functions. So you could look at the graphs. You could look at if you look at points on the graph, check out some points here, right? This point there at 3, -5. This point here, 5, -3. They're flipped. I could find more points here. There's a point here at 28, 0. Here's a point at 0, 28. They're flipped. That's how inverses work. So, a couple ways to solve that one. Right. Okay. Identify the following attributes of the inverse from part 3 above. Okay. So this one, right? This is the parent function, the parent square root function. Y equals x, root of x, square root of x. What are the transformations of this? So transformations again. So did you shift right? Did you shift down? What did you do? Let's look at it. Let's just look at it. Let's clear some of this. Let's get rid of it. So in the same way, you got it should be y equals a times the square root of x minus h plus k. Can I do that? You've said to me? H is not. H is a function. Try using parentheses. Where's H function? Okay. Let me get rid of this. That's fine. You don't want me to be here? There we go. That was the issue. Okay, so this is, again, this is your squared function. H should be 0 at first. K is 0, right? And I want this to equal, y equals, here's sqrt x minus 3 minus 5. Right, this is what it was before. Let me do this. So again, the red one is the parent function. The black one is our inverse function here. So the transformations is this moved, well, it moved 3 in the positive direction, and it moved 5 down. Right, that's you can see it transforming. So again, from the parent function, right, you can actually see it moving. It goes 3 in the positive direction, and then it goes 5 down, 5 down. So the transformation went shift. That shifted over 3 in positive direction, and shift down, shift vertically 5 in the negative direction. Negative direction. It went 3 to the right and 5 down. You know, there's a lot of different ways to say that. The vertex is going to be at, if you just compare it, this is the vertex here at negative 5, 3. This vertex is at 3, negative 5. Just the opposite. And again, as we to show here what we learned, domain and range of the first function is the flipped for the other one. So without really even looking at it, the domain should be from 3 to infinity, not including infinity, but including 3. The range is all real numbers. That's just, I'm just flipping the values from the other one. And you can graph it. You can graph it and just double check. Right? Again, here is our graph. It should look something like this. If I actually include the negative. I mean, the square root function, I don't know if it really, you could say it includes the bottom. I would include it. We don't, it depends how you think about the function, because now this isn't a function, but I would include it. I would say the domain, domain is, again, from 3. 3 is the lowest mixed value, all the way up there. You can keep going forever. And yeah, the range is all real numbers. That's right. Part 5, graphing on the same set of axes. Okay, so let's do that then. Okay, so again, that's just the same graph we have here. If I put this back up here, get rid of that. That one. Right, that's what we saw. This wants to graph this. It's easy to look at it from Desmos and get some good points. So again, our vertex here was some good points. So negative 5, 3, it's going to be 1, 2, 3, 4, 5, 1, 2, 3. Oh, you can't see that. Negative 5, 3, there's that point. Go over 1, up 1, both sides. You can go from the vertex over 2, up 4, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. You can go over 3, up 9. I don't know if we can fit that. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. It'd be like a little bit over. Right, so there's that one. This is f of x. Again, notice you have the vertex is at negative 5, 3. So just go over now, flip it. Go over 3. 1, 2, 3. 1, 2, 3, 4, 5. That's going to be at 3, negative 5. Right? There's, you just flip these points. So go up 1 over 1 like this, down 1 over 1 like that. from that vertex up 2 over 4. 1, 2, 3, 4. Down 2 over 4. Up 3. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is f inverse of x. So there's the graph, right? Because again, you see, I have to draw like this dashed line here. You can see how they're kind of inverse of each other. All right, last little thing here. Usually when we find the inverse of a function, the domain range gets switched. Okay, why did that not completely happen? Okay, so now I see what they want. Okay, so you might want to, it depends. Technically here that this graph should not include these points here. If you want it to be a function, you should not include these bottom points here. It should just be that one like that. Technically, I forgot about that. So that's going to change a couple things. So the range is not actually all real numbers. It really should be. The range should be, the low point is -5, right? The low y value is -5 and above. It should be -5 to infinity if you're going to go that way. You know, I'd say because maybe why is that? Because there are the square root function. I guess maybe there are tricks in the square root function. The square root function doesn't include the bottom part because then that wouldn't be a function by definition of a function. I'm trying to think of the way I'd word that. So I would not really graph the rest of this. Don't graph that, or just make notes. It should only be this. It should have that line there. Why that happened? I guess maybe there are restrictions on the square root function. I think that kind of makes sense. They're squaring the functions. Maybe if the domain and range fully switched, f inverse of x would not be a function. Something like that. It wouldn't be a function. Just to kind of think about this a little deeper, let's, again, I'll do this on scratch paper. So why don't we have this graph here? So our inverse function again was this, right? Square root x minus 3 minus 5. That was our function here. And we say, oh, you can't have a point. So say when x is what's it mean? 1, 2, 3, 4, 5, 6, 7. When x is 7, what's f inverse of 7? 7. The square root of 7 minus 3, that's 4. It should be, the square root of 4 is what, plus or minus 2? It should be plus or minus 2 there. That's why we get this 2 points. It should be a point at here and here, but they only take the positive square. They're only taking the positive square roots here is what they're doing. There's a better way to explain that. I'd have to think about it a little bit more. But the reason why we don't have both these graphs is if they were graphed, then it wouldn't be a function, right? If you had a point here and a point there, it doesn't pass the vertical line test, and that wouldn't be a function. So that's kind of why there. Okay, so main takeaways. The main takeaways from a thing like this is the relationship between domain and range with a function and the inverse function. That's important to know. Yeah, that's important to know. How to find the inverse by swapping x and y. That's an important thing to know. And yeah, that's most of that one. That's all that one. How long How long am I actually taking? Sorry if this taking a long time. I wasn't even checking time. 40 minutes. Ugh. That's basically what you pay for a tutor session. So 40 minutes. If you have more questions, email me. But that is that worksheet. Again, big ideas are completing the square. That's a big idea. Make sure you complete the square. Yeah, I'd say that's mostly it. Cool worksheet. Fun times. I enjoyed it. I'm teaching Algebra 2 right now at McCallum, but we haven't quite got this far yet. You're doing more fun math, so you're lucky. You lucky dog. A dog you. Okay, so that's that. Email me if you have any more questions. Have a great rest of your day. Merry Christmas, Happy Holidays, and whatnot. I'll see you later.